Dear friends and members of the KITION Planetarium Observatory, I would like to welcome you to our online Science Café. Tonight, we are very honored to have as our guest speaker, a great honor for us, as I mentioned earlier, a friend and colleague and Executive Director and CEO of the American Association of Variable Star Observers, Dr. Stella Kafka. As you know, since January, we have been holding all these meetings, and every 2 weeks we have these meetings. And, from this month onwards, we will be doing it on the last Tuesday of every month. Now, the abstract for tonight is related to Betelgeuse. In October 2019, astronomers noticed that Betelgeuse entered one of its dimming episodes. Nothing unusual with Betelgeuse. Betelgeuse kept dimming past its known recorded minimum brightness. From the seventh brightest star in the sky, Betelgeuse eventually became the 21st, puzzling astronomers worldwide. So more about this we will hear today from Ms. Stella. Dr. Stella Kafka is the Executive Director and CEO of the American Association of Variable Star Observers. If you're observing variable stars, for sure you know her. I know her many years before she was actually, I've heard about her before she went president, because I was communicating with from the early stage of our science center with the previous president of AAVSO. And when I saw the Greek name, I was really excited and enthusiastic about it, and I took the initiative to invite her to as a guest speaker. So this international organization is focusing on engaging professional and amateur astronomers in science. Within the auspices of the AAVSO, Dr. Kafka is working towards enabling individuals from all backgrounds to actively participate in research projects, building a community of science-savvy citizens who work collectively to understand some of the most dynamic phenomena in the universe. Dr. Kafka acquired her BSc in physics from the University of Athens. That's why I gave her the regards of Dr. Xenophon Mousas, a very good friend of us. And her master's and PhD in astronomy from Indiana University in the States. Her research interest is semi-detached binary star systems, the cataclysmic variables, which can become supernova. IA. Okay. More information you can find on the link. You can. I will share with you the link in the chat if you haven't entered the chat, and you can learn more about her work, and she will tell us more about it during her speech. So, Dr. Kafka, thank you very much for doing us this honor. We are intrigued, and we are eager to listen to what you have to say, and we are very happy to have you with us. I would also like to welcome all our friends who joined us tonight. Thank you. Stella?
Wonderful, wonderful. Good morning, good afternoon, good evening, where you are. As my colleague mentioned, my name is Stella Kafka. I am the Executive Director and CEO of AAVSO. And here's a fun fact from me. I was born and raised in Athens, Greece. My mother is from Cyprus. She was born in Fidi of Paphos. And I actually spent a lot of my childhood summers in Cyprus. So I'm very close to your beautiful island. I'm looking forward to going back once we are back from being stuck inside from COVID. Another thing I would like to mention is that thanks to technology, I know that we're all zoomed out. I know that it's really frustrating to actually talk to each other through a screen. But if not anything else, social distancing is not translated to social isolation. We can actually get together and explore the night sky and discuss items of interest and keep ourselves sane. So today I'm going to talk about Betelgeuse. Here. Can you see my screen? Thumbs up or
Yes.
down?
Yes.
Awesome. I'm going to discuss a very interesting star that is actually one of the brightest stars in the night sky, one of those cases that we thought we knew everything about. But before I start, I would like to acknowledge about 1,500 observers who have provided observations on this star over the years, a work that was critical for the science I'm going to discuss today. And without this work, this science would not be possible. We wouldn't have noticed that there's something peculiar in the behavior of Betelgeuse without these observations of those individuals. So I would like to start by reminding you that the AAVSO was formed out of Harvard College Observatory in 1911. And actually, we are celebrating 110 years of our anniversary this year. And the purpose of founding the AAVSO was to coordinate variable star observations for the observatory director, Edward Pickering. As such, in principle, the AAVSO was the first association that was founded in order to connect professional and amateur astronomers and help them collaborate on scientific projects. This is a snapshot of our incorporation document to the state of Massachusetts, stating that the AAVSO was founded for the purpose of promoting variable stars and kindred objects. Even at the beginning of last century, our forefathers realized that there may be more types of variability other than stars. And they wanted to make sure that the AAVSO is involved with all types of scientific projects that would be of relevance and interest to our observers. So other than variable stars, we're also studying extrasolar planets. We're studying, which are technically not stars, right? We're studying black holes and neutron stars and cataclysmic variables, which are technically not stars. They're dead stars, et cetera, et cetera. Now, the AAVSO community is truly international. For those of you who are in Greece and in the UK and the rest of the world, hello, Europe. We are all over the world. We have individuals from more than 50 different countries. And as a consequence, we have a very diverse community. This translates to serving people with different needs, different priorities, different professional preparation, habits, and cultural backgrounds who are united under the international umbrella of astronomy. We have individuals who are interested in using variable star data for their research projects. We work with educators who introduce astronomy to their students. We collaborate with a very dedicated group of volunteers. We communicate with individuals who are interested in learning more about new discoveries and progress on variable star research. People who actively support citizen science and believe in our mission. People like you who are just curious to see what's happening in the night sky. And of course, we collaborate with our observers, those who acquire data through their telescopes, CCDs, DSLR cameras, and share this information with the wider community through the AAVSO International Database. But before I start with Betelgeuse, I would like us to play a game. How about a game? Yes, no, oh no. Well, you're muted, so I can do whatever I want. So here we are. Here is the game. This is a part of the night sky. Right? Every single dot that you see here is a star. Bigger dots are brighter stars, smaller dots are fainter stars. And what I'm interested in this case is to assign a number to each dot that represents its brightness. But because it's my game and I make the rules, I'm going to do things backwards in the sense that the brightest star will be assigned the smaller number that will represent its brightness. And with that, the faintest star will be assigned the larger number that represents its brightness. So with those rules of the game, this is number 51, number 91, and for that, number 64, 61, 75, 85. Yes, no? Thumbs up, thumbs down. Nods, something. I cannot hear you, so I hope you agree with that. These are the rules of the game. And this is
sorry, Stella, we may use chat.
You can definitely use chat because I will ask for your feedback. There is a star here that I'm going to call Maria because Maria is a beautiful name. It's my best friend's name that does not have a number assigned to it. And I would like to know what's Maria's brightness that on June 10th. What number would you assign to Maria with respect to the other numbers in its vicinity? You can use a chat. All right, I see a 62. I see a 62. So the way that we do that is Is it brighter or let's use actually, can you use the motions? Thumbs up or down? Yes? So for example, is it brighter or fainter than this? Brighter goes up, fainter goes down. Is it brighter than 51?
Yes, now, correct.
Okay, unmute. I would like you all to unmute, really.
Okay.
This is gonna be fun. Brighter or fainter?
Fainter.
Right. Brighter or fainter than 91?
Brighter.
Brighter and fainter than 85?
Brighter.
Brighter. Brighter or fainter 75?
Brighter.
How about 64?
Brighter.
It's brighter than 64, yes. How about 61?
Same.
Maybe a little bit brighter, a little bit fainter, so it's somewhere around there, yes? So I go out a different night, and here's the same stars in my sky, and here's Maria this night. How bright is Maria this night? And perhaps we can go again with the chat. So we're doing exactly the same, brighter, fainter than 51. It seems that it's fainter, right? Brighter and fainter than 61. How about 75 or 91?
Fainter.
Give me a couple more. It's closer to 91, right? This time. How about Maria this night, a third night? Ah, now I'm cheating you, right? So what number would you assign this time? Is it brighter or fainter than 51?
Fainter.
It's fainter. How about 85?
Brighter.
Brighter, definitely.
It's brighter. How about 91? Oh, well, it's brighter than 85, so it's going to be brighter than 91. How about 61?
Dimmer.
Fainter.
How
Yeah.
about 64?
Very close.
Yeah. So it's about 62, 63.
Yeah, how about 75? It depends on your eyesight, right? And you could always argue, it depends on what kind of conditions of observing you have. But yeah, we'll give it a 60 something, 65, say. Maria is a variable star in the sense that every time I go out and observe that particular star, its brightness is changing with respect to the stars in its vicinity that are not variable. And by the way, congratulations, you just built your first light curve. So light curve is the tool that we're using in astronomy in order to study variable stars. And all that we do, everything we do is exactly what we just did in that game. We actually compare the brightness of a variable star with time, we record it, and we just keep monitoring it with time. And from the shape of the light curve, we get information on what type of variable star this is. And here's another example. This is a variable star, light curve of a variable star. Again, brightness change with time. And this would be the light curve of a non-variable star. So it doesn't do much with time. You can take this kind of data with any means you have in your hands, as in your binoculars, your DSLR camera, your CCD camera if you have one, but just even with your eyes, you can make this measurement the same way that I just showcased in the game. Here's another example, one of my very favorites that showcase stellar variability. This is what we call a star cluster. So a star cluster is a family of stars that were born all together at the same time, but with different masses, so they evolved differently. And pretty much what you see here is a collage of 4 different images, digital images that were created into a movie. So we circle around those 4 images again and again. They were taken the same night. You see the center of the globular, it's the globular cluster. The center of the cluster is here, and its density is getting less and less as we go further away from the center. And most of the stars are not doing much, they're just hanging out in there. And they're bright and they're pretty. But if you pay very, very close attention, you'll see that there's some stars that are blinking. Can you see them?
Yeah.
This is not an atmospheric effect. This is a real effect. Can you find the variables? These are the stars that are changing with respect to the rest of the stars. There are variable stars in this particular cluster. So stars can change their brightness within the same night. And depending on what the light curve shows, we actually get to understand how they change their brightness, what type of variable stars they are, but the nature of variability. Now, the star of today's discussion is Betelgeuse. This star belongs to the constellation of Orion, a constellation that is part of the Northern Hemisphere winter triangle. That is Orion, Canis Major, Canis Minor. According actually to the Greek mythology, Orion is a big giant, a big hunter, and he has two dogs, which is actually Canis Major and Canis Minor, the big and the small dog. And actually Betelgeuse is on the shoulder or armpit of the giant, of the hunter, as he kind of raises his hand to hunt in the universe. So this is pretty much how ancient Greeks imagined the whole constellation of Orion, where Betelgeuse is. Now, a couple of facts about Betelgeuse. This is the 6th or 7th brightest star of the night sky. It is an evolved star, so it's past its adulthood. It's what we call a red supergiant. It's 700 light years away, which means that light emitted now from this star will take 700 Earth years to travel to Earth, to get to us. And its mass now is 12 solar masses. So as an evolved star, it lost some of its mass at some point. Its radius is about 880 radii of the sun. And exactly because it's very close by, we have means of taking pictures, real pictures of the surface of the star. So this is a real image of how Betelgeuse looks like. And if you put the sun in the very center, this would be the size of the Earth's orbit. This would be the size of Jupiter's orbit. And this is the size of Betelgeuse. So just imagine a star of 12 solar masses as, with a radius as large as the distance between the sun and Jupiter. Not only that, comparing to the sun in terms of mass and size, it's really huge. This is the second largest star in our Milky Way galaxy after Antares. And just in case you're wondering, there is a little dot here. It's not on your screen. It's a little dot that pretends to be the sun. So this is Betelgeuse. What's most important for our purposes is that it's a variable star. And it's actually what we call a semi-regular variable. Now, how do we know that? From the light curve. This is a long-term light curve of Betelgeuse, an AAVSO light curve, more than 100 years of data. The earliest points actually are around 1800. And what you see here with dark points are visual data that were acquired by people just using their eyes. Back then, there was not that much light pollution around. But even later, individuals were observing this star with their eyes as well, just taking visual data because it's really very bright. What you see with green points are actually digital data, once digital means became available to non-professional astronomy. So what do I mean by semi-regular variable? Semi-regular stars are evolved stars. So these are giants or supergiants that are showing some sort of periodic change in their brightness, accompanied or sometimes interrupted by various irregularities. So fine, we can see all this kind of variation in the light curve of Betelgeuse. We know it's semi-regular, it fits within the category. What's the issue here? What's the problem? Well, look at the light curve. We're talking about more than 100 years of data here. It does have its up and down, but these ups and downs are confined within this range, right?
Вы можете...
Beg your pardon?
Sorry, it's okay.
So what happened in October 2019? Why was it special? Well, in October 2019, the star began dimming and dimming more than we were used to until it became the 21st brightest star by December 21, 2019. We had 120 years of data, and this was the first time that we saw this kind of variation, this kind of change in the light curve of the star, the behavior of the star. Something happened. And actually, I'm just going to zoom in here, only in the digital data, and show you the recent years of Betelgeuse. Again, this is the range of variation. And here's the event of December 2019. And what's very interesting is because Betelgeuse is one of the brightest stars in the night sky. It's beautifully demonstrated in the winter. You can see it very clearly. People really, really noticed. Here's Betelgeuse in January 2019. Here's Betelgeuse in January 2020. So if I am to blink back and forth between the two images, nothing else changes. Betelgeuse did. The whole constellation changed. The change was extremely noticeable. And actually the only way of figuring out what was going on was actually to take a step back as professional astronomers who had access to a whole bunch of data and take a look at the history of the star and try to understand a little bit about Betelgeuse itself, what we know about it, and whether what we know fits in the big picture that is fits in this particular picture of the fainting of Betelgeuse. Yes, people called it the fainting of Betelgeuse. So somehow Betelgeuse fainted. So here's what we know about Betelgeuse. We know that it's an evolved star, right? It's a giant star. It's an aged star. This is a star that expanded because it has exhausted the fuel in its inner core. Our sun will become a red giant in 4 or 5 billion years from now, but Betelgeuse started its life as a much more massive star. It started its life as a star with about 15 to 30 solar masses. And then after it moved from the main sequence, after it evolved, it got rid of most of its outer layers, and ended up as a 12 solar mass star, the star with the mass that we see today. What we also know is that in this supergiant phase, during which stars lose so much mass, what we see is a remainder, like a leftover core. And during that particular time, those stars are extremely bright. And not only they're bright, they release copious amounts of light in the forms of photons that zoom outward in all directions. This light is pushing considerable mass outwards in the form of grains or dust. So those particular stars have episodes of dust ejection from them. We don't understand why, we don't really know why, but we know that they happen. And actually Betelgeuse itself has been captured to have such an episode. What you see here is a real picture that was taken from space by the Herschel Observatory in 2012. And what you see here is in infrared wavelengths that captures more dust, colder material. These shells indicate asymmetric mass loss from the star that expanded in the cold universe and condensed and became pretty much dust. That's one of the things that we know, that those things have dusts. Here's the second one. We know that Betelgeuse's atmosphere is highly convective. This is not unusual. Convection is pretty much ubiquitous in stars. And where do we know convection from? The sun, our own star. If we dissect the sun, here's its core and here's its outer layer. Convection happens in an external layer here. And it manifests itself as hot material moving towards the surface, cooling down and sinking at the bottom of the layer where it's heated again. It just moves this way. This is very analogous to boiling water or boiling soup. I'm pretty sure that you've seen it before, right? This is our best example when we're discussing convection with our kids, for example, just boiling water. It's really, it's getting heated up at the very bottom of the pot. It goes up, it cools down, it follows gravity, goes back down. So pretty much this is what's happening in the sun. Now, the cool thing actually about this star is that it's so nearby, the sun is nearby, that we can actually take real movies of convection and see how it works. This was taken with DKIST. It's a 4-meter solar telescope in Hawaii. It was part of the commissioning of the telescope 2 years ago, and it showcases convective motions at the outer layer of the sun, our sun. Now, we know also that convection is similar in red supergiants. This is a numerical simulation. This is a model, not a real picture, but this is based on the physics that we know. This is a reconstruction of what's happening in Betelgeuse. And what it shows here is that there are convective patterns on Betelgeuse's atmosphere. Dark areas here are cooler and bright areas are hotter. So in this case, hot, bright material rises, it cools down and sticks deep in the atmosphere. And what we know from the data, from the long-term data, is that there are two different timescales for convective motions on Betelgeuse that are much more prominent on the light curve of the star. The first one is a long one. This is pretty much, again, some of the data of the AAVSO. And it can't be, this first convective motion can be detected only by the analysis of this long-term light curve. I just overlaid some blue lines on top just to guide your eye on this particular long-term modulation that we know that leads to an increase and decrease in brightness every 5.9, every about 6 years, more or less. The second modulation, the second time scale is much shorter. Is this modulation that we see in the annual light curves of the star? And if you take all the years together, we see that this particular time scale lasts for 425 days. They're both due to convection. So these are the things that we know about Betelgeuse. Can any of them give us an explanation of the dimming in 2019-2020? And at that time, there were two dominating theories. The first one says that, maybe what you have here is a coincidence of the two convective timescales. When you have a minimum of the 425-day dimming, you have a minimum of the 5.9-year dimming at the same time. So the star goes down and then it dims even more. So if that's true, then you will have a huge dark spot that is covering part of the atmosphere of Betelgeuse, and that would be the cause of this dimming, right? And as every good theory, this one had a test. It says is that a prediction, if we go and observe Betelgeuse, the atmospheric temperature will be lower at the minimum, as the star outer atmosphere will be dominated by the cooler dark spot, and that the brightness of the star will recover by the beginning of April 2020. Very specific prediction for this particular theory. Now, theory number two. Well, how about Betelgeuse had a very unusual asymmetric dust episode, consistent with what we know about stars like this one. And in this case, dust acts usually like a blanket, and that would obscure part of the star's atmosphere and result to the observed drop in brightness. This comes with prediction as well. We will see somehow dust around the star at the time of the dimming, and the star's brightness will recover when the dust dissolves. So at that point, all we did was just sit down and try to gather more data. It was a very interesting experience. They had astronomers, observers all over the world, and professional astronomers all over the world asking for data. And we all kind of were wondering what Betelgeuse would do. This is an exercise in patience, my friends. And actually, guess what? Betelgeuse's brightness recovered in April 2020. Does this approve or dismiss any of the two theories I showed you? Yes, no? The answer is no, actually, because the fact that it recovered in April doesn't mean that either of the theories were correct or wrong. They both predicted a recovery at some point. So the good thing with Betelgeuse is that it's a very popular star amongst professional astronomers. And while our observers were taking ground-based data on this particular object, professional astronomers who had access to much more detailed, much more specialized instruments were actually pulling out favors and observing the star with whatever means they could. And there were two different studies that came out last year, or actually this past summer, that provided some kind of explanation. The more coherent picture came through a synergy of the AAVSO and the Hubble Space Telescope. And that is because the AAVSO observers were observing while the Hubble Space Telescope were taking snapshots using a UV instrument. And because of this kind of synergy, there is an interpretation of the data, a very consistent interpretation of the data that I'm going to present to you here. I'm going to show you a schematic that is summarizing several months of Hubble's UV spectroscopic observations of Betelgeuse beginning in January 2019, and it yields a timeline leading up to the dimming and recovery. So this is a 4-panel graphic that it illustrates this effect. What's happening here, the first two panels, as seen in the UV light with Hubble Space Telescope, you have a bright, hot blob of plasma ejected from the emergence of a huge convection cell on the star surface. So as a result of convection, there was a huge blob that was pushed outward, but it was really large, and because of inertia, it was pushed outside the star. It didn't just emerge as a hot spot, as a cool spot. Here, it shows that this blob of plasma, as it went, as it was pushed outside Betelgeuse, it cooled down. And as a result of cooling down, it created dust grains. So it became a blanket as seen from Earth. And actually, this particular panel shows how we see Betelgeuse, or we saw Betelgeuse in that particular episode, covering part of Betelgeuse's surface, outer atmosphere. So it seems that an extensive dust episode is the primary cause of the dip. Doesn't really mean that convection did not play some role, but in this particular case, it seemed that it was dust. The cool thing is that there was another study that came out of stereo. This is a VLT, an instrument, one of the VLT, very large telescopes from ESO, and again in synergy with the AAVSO. While we were taking data, they were observing Betelgeuse. And what you see here is that it's, you see snapshots on the light curve when stereo was observing, and it was mapping the surface of Betelgeuse itself. So you see this dark spot that was covering part of the starlight. It's very asymmetric, and it's very unique as far as we know. So where are we now? Well, Betelgeuse recovered, and now it's just hanging out. And pretty much, it seems that it's lazy this year. There is much more to understand, but data is being accumulated every day. And it's we keep observing this particular star because you never know what's going to happen. Now, here are a couple of other things that emerged from our discussions from the dimming of Betelgeuse. You know, 2019, 2020, when Betelgeuse was going down, it was recovering, all kinds of activity was happening. I was getting lots of phone calls from individuals and emails asking me whether Betelgeuse is going to become a supernova, whether this particular light curve behavior is connected with a star like that becoming a supernova. Because according to its evolutionary stage, the next step is a kaboom. The estimated time for Betelgeuse to become supernova is within the next 100,000 years. But at this point, no one knows what a star does observationally right before it goes supernova, because it's never been observed. This particular dip likely is not connected with the fate of the star, but who knows, right? Another thing to think about is what would be the fate of the post-supernova remnant. So there are two different avenues. The Betelgeuse, after becoming a supernova, it can become a neutron star or a black hole. If the mass of the remainder object is less than 2 to 3 solar masses in the central region, then Betelgeuse will become a neutron star, and it will appear as a pulsar as seen from Earth. If the explosion remains are more than 3 solar masses, then the central region will become a black hole. So we'll have our own black hole in our nearby neighborhood from Betelgeuse. But you know what's really cool is that the whole dimming and / future supernova Betelgeuse story triggered the imagination of people, and especially artists who made assumptions of how Betelgeuse will look like as a supernova in our night sky. So this is Orion as we used to it. This is Orion's belt. This is Betelgeuse here. And when Betelgeuse becomes supernova, it will look like this. Speaking of light pollution, here you are. There's another star, another object that would be as bright as the moon. So hang around for a couple of hundreds of thousands of years just to see one of those spectacles. Really, really majestic. Now, here's another question. Is Betelgeuse unique? I hope that you know the answer here. It's not unique. The estimated supernova rate of this type in our galaxy is 3.2 per century, and we haven't seen one for a century. So does this mean that we will live to witness one? Well, maybe, but what if what happens? Can we predict it? It turns out that we can't predict it and we can't observe it. So the AAVSO right now is involved in a project with what we call a supernova early warning system. It turns out that when one of those stars, which are very similar to Betelgeuse, becomes supernova, the first type of particles that escape from the core, even before photons, are neutrinos. Those are very high energy particles that reach the Earth hours or even days before the light escapes and gets to the Earth. But detecting the neutrino burst from a certain part of the sky, if you know where to look, astronomers can actually notify observers all over the world to go observe the candidate stars, one of which is the source of the supernova. So right now, we have a number of stars in our pocket, let's say, in our galaxy, most of which are long period variable stars. And they're like Betelgeuse, like Antares, for example, or VV-Ceph, who are very likely to explode within the next few hundreds of years. Now, out of all these candidates, we're hoping that one of them is going to go off within the next couple of decades. I know I'm telling you about long-term projects, but right now there is an international collaboration of more than 20,000 scientists from any neutrino detector that you can imagine, and the AAVSO, who are planning, best practices to actually monitor this, the sky, the night sky, for neutrinos. We know the specific type of neutrino ejection, and that results from a supernova eruption. And based on that, they will notify our observer community to actually observe at that part of the sky, not just a part of the sky, the candidate stars. There are about 200 stars. We are also collaborating with gravitational waves, LISA, LIGO, because actually gravitational waves are going to be emitted from a star that's so massive it's self-collapsing, becoming supernova. So at this point, we are at the point where we are trying to understand the alert system, and we are building a collaboration of observers who would actually receive those alerts and go observe the stars. So what I'm trying to say here is that if you have access to any instrument, even your eyes, if you can do this, pretty pictures, take data or anything, you can certainly help us understand this kind of objects by continuing monitoring them. And also, please join the SNEWS campaign. Join this collaboration to perhaps capture the once in a lifetime event. Actually, no one has ever seen anything like that before. This is how you can join us through our high energy network. Our observing section is actually leading this project. You can send us an email, avso@avso.org, expressing interest, and we can connect you with the right people. We have a SNEWS Slack channel. So it's a collaboration with the SNEWS team. We're still trying to get, they're still trying to get their tools together, but at the same time, we're going to start with fire drills to make sure that our observers are prepared and the alert system is in place. If you need help, if you need resources to get started with your observation, the AAVSO is here for that. Go to our webpage, scroll down. We have a whole bunch of resources for you. Here's where our observing sections are. Here are tools for our observers and a whole bunch of educational material, most of which is free and translated to Greek and can be downloaded and used as you see fit. A plugin here, we are celebrating our 110th year of Citizen Science 110th anniversary next week. And you're very welcome to join our celebration, our annual meeting and celebration. And actually, one of our special keynote speakers is Dr. Andrea Dupree from the Center for Astrophysics from Harvard, who was leading the HST campaign. She's the queen of Betelgeuse. If you want to hear more about Betelgeuse, what's happening now, what's going to happen in the future, she's the person to actually talk about that. So she's going to be there. She's going to be our keynote speaker. And also join us for a spectroscopy workshop that's going to start on the 3rd of November, 3rd and 4th. It's going to be hybrid, in a hybrid mode, and it's going to be addressing, if you want to do spectra, it's going to be addressing your needs and help you get started with that. You know, I'd like to leave you with some final thoughts here. We live in a renaissance of variable star astronomy. There's so many space and Earth missions that aim at exploring the night sky, and they will produce a lot of mysteries, a lot of stars that we just don't understand, a lot of stars whose behavior we thought we knew, but voila, it surprised us. And there are not enough professional telescopes to acquire the data needed to help solve these mysteries. Small telescopes like the one that you have in your observatory in Cyprus, or the one that you might have access to in your backyard or through your astronomy club, can't be used to follow those stars, to follow those mysteries and give answers. We really need you. We need people like you to probe the universe. So I hope that you will consider at least joining the fun. With that, I would like to give you, here's our webpage. If you want to see more information or get more information, training material, education material, a link to our annual meeting, lots of announcements this time at this annual meeting. I'm not going to tell you yet, but we have lots of exciting things to share with the community. Please, please, please become a member. It's $85 a year, right? And it's really supporting us. We are a nonprofit organization, so would love to actually get support from you. And if you have any questions, please contact us, aavso@aavso.org, and we are on social media as well. And with that, I would like to thank you for your attention, wish you clear skies, and ask if there are any questions for me.
Well, Stella, thank you very much. It was a very interesting and very informative presentation. It was good that we saw both theories, and it actually proved that it could be any of the two, or it could have not been any of the two, which was really, it brought light to many debates that were held online and among astronomers and amateur astronomers. It was amazing. Guys, any questions for Stella?
I was going to ask one, George. During the sort of the theory of the dust, would doing spectrographs show a difference in the makeup of the star at those times?
So there were actually in our data spectroscopy database, we have spectra of Betelgeuse during that time, and you could see some changes in the red because dust actually affects red wavelengths. Being a red supergiant, Betelgeuse has a lot of titanium oxide in its atmosphere, and you could see even the TiO bands towards the red, the very edge of the spectrum kind of dimming. It's very interesting.
So did that give more credence to the theory that it was something like dust that was in the way, or? No,
my friend. It's exactly because it's at this point, based on the more detailed data, we believe it's a synergy, let's say, between convections and dust. Here's another thing I didn't tell you. Stars like Betelgeuse are fully convective. So the convection zone goes all the way to the center. So if a huge blob of plasma was ejected, it came from the center and pushed outwards. So it's a synergy between convection and dust that created, it's like a cause and effect sort of thing that created this particular episode. Having said that, A, we need more data, and B, we need to understand a little bit how frequent these phenomena are. Because remember, this is an asymmetric dust episode that was pushing material towards us. We don't really know if such events were happening away from our line of sight, in which case we wouldn't see them. You know? So maybe we didn't miss them, but the light that we're getting is partial. It's what we can see, right? It's a three-dimensional object, but we see a projection in the sky. It's a two-dimensional image in the sky. So these are questions that need to be answered. What I find fascinating is that we have, again, as I said, we have data since actually it's more, 140 years of data in our database. And this is the first time we see something like that. So we're learning new things about old favorites. It's really awesome. Yep. Keep looking up. You never know what Betelgeuse will do next time. I mean, I had people come into the last conference before we shut down for coronavirus, January 2020. They were coming through the AAVSO booth and they were asking me, what's wrong with Betelgeuse? And I would take it personally. I didn't do anything. I have no idea what you're talking about. But it was spectacular. You could just see it becoming fainter than Rigel. So it changes even the constellation itself. It was spectacular. It was beautiful.
May I ask one question? It's about future of Betelgeuse. So first of all, I wanted to mention that KITION Planetarium and Observatory contributed into Betelgeuse observation as well. So among those many thousands of observations, some of them were supplied from here, where we are now. And in addition to this, we keep, for example, the Sky is Alive course, where we help methods of astronomers with contribution to science. And one of topic is variable stars, and we help them to do their own observations and supply them to American Association of Variable Stars Observers. So, okay, it's a background. Now it's question about possible future of our star. So suppose I mean Betelgeuse. Suppose that it will become pulsar, and in this case, is there a chance that the ray, when it rotates, will pass through the Earth, or it will go another place?
No, we might be able, because pulsars, neutron stars are very, very dense, but very small. So we won't be able to see anything from here in terms of its X-rays, but we would be able to observe it from here. It will be a beautiful radio source, maybe X-ray source.
I mean, will the being pass through the Earth, or it's not known yet? It's
not known, but even if it depends on what's the rotation, what's left, right? And how it will actually, by the kick velocity, how it's going to be oriented. But at the same time, it's not going to affect us. Even if the beam points towards us, it's not going to do anything. We won't even see it as such.
Okay, some other questions?
Personally, I vote for a black hole, but hey.
I will go for the black hole as well.
Yeah.
Okay, some more questions? I have one more question. It's about neutrino. In 1987, 23rd of February, there was a supernova in Magellan Cloud, and that time they observed neutrino outburst as well in Neutrino Observatory. And how it was connected, I mean, the time. So when as far as I remember, it was first they observed the supernova, and after that they registered neutrino. So
I think it was
is
the
it
other way
correct?
around. It was more coincident. So by that time, they did have a lot of neutrinos, but they did not connect it necessarily with the supernova. There wasn't a telegram that went out in all observatories. And actually the person who discovered the optical light was a telescope operator at Cerro Tololo Inter-American Observatory, who actually found this person. Yes, there was a link afterwards. And that's actually how we sort of know what kind of emission to expect from a supernova. Completely coincidentally, and this was an irregular supernova. It's like nature's playing a game at us. But as far as I remember, neutrinos came first.
Okay, thank you.
But within, neutrinos, that was a blue supergiant. It was a little bit different than that, right? So neutrinos came almost at the same time. Kind of, it was a different sort of explosion in this particular case. That's why the assumption here is that neutrinos may come within hours before the first light. So we need to jump on target as quickly as possible. And that is why we started working with the SNEWS team as early as now, pretty much, to actually prepare observers to observe this kind of episode when it comes. There will be a very interesting presentation at our meeting by one of the SNEWS team members talking about the connection with neutrinos and what we can expect. But at the same time, until we see it, it's all speculation. We're just getting ready, right? So if you sign up and join us, just be prepared for something really fun. And if it wakes you up at night, just get up because you don't want to miss that.
Thank you.
More questions? Well, if there are no more questions for me, George?
We will talk later about the professor's career and try to involve some students in the observations. We try to create a team, and now with the new telescope that we set up, things will be much better because we had a problem with the tracking with the other one. We have the 16-inch telescope here that we'll probably install the other or the 14-inch one. So we'll be able to do better work in the near future. And we want to devote part of our time to research variable stars in cooperation with AAVSO. So
we're really looking forward to your data, and we're very welcoming anyone's contribution, actually. We, as you can tell, it takes a village, right? To build a cool light curve. And you never know which star is going to surprise you. That's why we call them variables, they change. So with that, thank you so much for having me today. I hope you're all safe and healthy and strong. And I hope that at some point in the future, we'll get to have some coffee together.
Great.
Thank you very much for the lesson,
Thank you so much for coming.
So, guys, our next event, our next meeting is going to take place on the 30th of November. Alexander, may I share my screen, please?
I think you may.
You're already sharing your screen.
I should close mine. Okay, let me stop.
Okay. Okay, our
same login details for next meeting.
Yes, our next meeting on the 30th of November, the same time, 8 o'clock Cyprus time, UTC +2 then. We will host our first Cypriot analog astronaut who participated in the lunar mission, and was the first one from Cyprus, and actually one of the first groups they did their lunar expedition last week regarding time and space isolation. So they did a lot of experiments regarding every time they were changing their time zone, every time they are waking up at time 0, so they had to rearrange their brains to adapt to the new time. They had to make some experiments with their beds, how to cover themselves to see how that affected their sleeping time. Those of you who participated in our International Observe the Moon Night online session, we had the chance to speak with all of the analog astronauts online through the Zoom meeting. It was the first time it was done worldwide, and they did a second session after us with a NASA workshop, if I remember well. So she will give a talk regarding their participation in the lunar analog mission and their main experiment, which was privacy in space. So she was going to be with us today, but it is International Astronautical Conference in Dubai. She included us, and I thank her for that in her presentation, and promoted KITION Planetarium Observatory work and science outreach and research. And I thank her again for that. So she's going to be our guest on the 30th. She's an astrophysicist. She graduated at the University of Glasgow. She's got a master's degree, and she's going to continue now with her PhD. The first analog astronaut center from Cyprus, Eleonora Kaiser. So looking forward to see you on the 30th. And I would like to express also the great honor and thankfulness of our team here at the KITION Planetarium Observatory, that we enjoyed this interesting talk, and the willing and the good cooperation with Stella Kafka, Dr. Stella Kafka, who gave us this presentation. We're looking forward for more in the future and more cooperation and collaboration.
Take care. Bye, guys.
Thank you.
Thank you, Stella.
Bye, guys.